Okay, so this time we're going to look at vibrations and sound. It's a follow-on to the chapter on waves, and it looks at waves and its connection with sound. So if we look quickly at the syllabus, we'll see first area, wave nature of sound. We look at the characteristics of note, resonance, and a few other things. This will probably take 2 videos. So, wave nature of sound. How do we know that sound is a wave? Well, first of all, certain characteristics such as it can be reflected just like light. It can be refracted. It'll change direction when it passes from one material to another. Light going through a glass block gets refracted. Sound going through a different material such as a container of carbon dioxide will change its direction. A balloon filled with carbon dioxide will act like a lens, just like glass acts like a lens for light. So that's refraction. Diffraction. Sound waves spread around corners. You notice that when somebody speaks to you from a room next door or something like that, the sound will spread around corners. And interference. And this is a key one. Only waves can interfere. So if we can prove that, we can prove that sound is a wave. And there's an experiment to go with this, which is in your book. We'll have a look at it here. Okay, so we have here set up 2 speakers, a little signal generator which is producing a note, a little amplifier and a battery to drive the speakers, and a separate one to drive the signal generator. So it's producing a note. And as I move across the speakers, listen carefully. You should have heard the note get louder and weaker. It doesn't die away completely, but it does change. It gets louder and weaker in a regular pattern. Listen again as we go back. If we do it with just one speaker, we don't hear that effect. So, what's happening? Well, if we look at this little demonstration here, each speaker is connected to the same signal generator, so it's producing the same note, and it's being emitted here. And as the waves come out from each speaker, they are overlapping. Just like we had in the chapter on waves, we have interference, and as somebody moves up and down, their ear will eventually arrive at a spot where there is destructive interference, the sound will be lower, and where there's constructive interference, the sound will be louder. So there's areas of loud and weak sound, and that's what they notice as they move along this section here. And that proves the sound is a wave because of interference. Again, if we look at your own book, this is done up here in the top right hand corner of the chapter 17 on whatever page it is there, you'll find it yourselves. And again, they have the same experiment and an explanation of it. So the waves spreading out cause interference patterns, and this, if you look up StudyClix, you'll see in Leaving Cert questions this has been asked before, being able to describe this experiment, draw a simple diagram of it, and say what it shows and what it proves. Okay, so interference of sound produces these loud and weak notes as we move in front of the 2 speakers, proving that sound is indeed a wave. All vibrating objects produce sound, like the tuning fork shown down here at the bottom of the page. This is page 189, I think, of your own book. So if we look at a little YouTube video back here, let's see, this one is from Slow Mo guys. They make videos on slow motion things, and they have a tuning fork, and they're bound to pop it in water, something you might have done in the first year. And you see exactly what happens. It proves that the tuning fork is vibrating. It's vibrating far too fast usually to see, but you see it, or see the effect of its vibration when it's put into the glass water. If we look at that in slow motion, this is what we see. First of all, you will notice the tuning fork vibrating. And when it hits the water, it throws up the water. So that's what's happening. So a tuning fork, which we know produces sound, is a vibrating object. So if we look back at the syllabus, we've shown that sound is created by vibrating objects. Speed of sound, well, sound travels at different speeds in different materials. The speed of sound in air is 340 meters per second approximately. It can change depending on temperature and other factors. In steel and in water it's much faster. So the speed of sound changes in different materials. Sound also requires a medium. Light will travel through a vacuum, but sound requires a medium. And if we look at this video here, we have a guy who has a bell jar and a mobile phone in the bell jar, and the mobile phone is playing a song. Now he pumps the air out of the bell jar, and when all the air is gone, you can no longer hear the sound. And when he turns, so no sound. But when he lets in the air, listen carefully.
Can't hear the music.
Oh my God!
So, okay, it's a faint video, but yes, you can hear the sound of the mobile phone. More importantly, if you're asked to describe an experiment to show that sound needs a medium, a description like this: bell jar, phone or other object that you know is vibrating or producing a sound. We know the sound is coming from the phone because we can see that it's set to play or whatever. Remove the air and see the effect. Okay, so sound needs a medium through which to travel. And again, that experiment is described in your own book on the top of page 190. And yes, you can look up YouTube and find some other videos and better videos and so on of that. We talked about the speed of sound already. It travels at different speeds and different materials. And we'll have a look at the characteristics of a note next. Here we have a signal generator, which is producing a note, which is displayed on the oscilloscope here. It's also connected to a speaker, so we can hear that note. Okay, we'll play it. So it's producing a note. Frequency 765 Hertz. As it goes up, notice what happens to the wave. At high frequency, there's more waves. The waves are closer together. So the pitch, that is the note, depends on the frequency. Right? We saw that the frequency increased as we looked at down here at the meter on the oscilloscope. We also physically saw that the display showed that the waves got closer together. And we heard the note change. So the higher the pitch, the higher the frequency, therefore the closer the waves are, the higher the note. So pitch depends on frequency. As I turn up the volume, watch the amplitude. That is the height above or below the center point for that wave. So increasing the volume increases the amplitude. So the loudness of a musical note depends on the amplitude. The pitch depends on the frequency. So high frequency there, 4 kilohertz, right, on that display. Okay, so that's two of the characteristics of a musical note. The last characteristic we're interested in is the quality. Why does a musical note from a tuning fork differ from that for a guitar or piano or something else? And the answer is that the other instruments like a guitar or a violin or a harp or piano or a drum not alone produces the note in question that we're playing, but it produces other notes along with it. These are called overtones. And when you hear them, all of these notes together give us the characteristic sound of that instrument. A pure note, like that of a tuning fork, is a perfect sine wave. So that's just a single note, somewhat like what we heard from the last experiment. But a guitar or piano or whatever produces the note that you're playing and other notes to a lesser extent. And the way they combine, and even vibrations of the material making up the instrument, like the wood of the guitar or whatever, add to the sound that you hear. So just like your voice, different people's voice contain different notes in them, and a display on an oscilloscope will see huge variation in patterns, and these are the overtones. So this is what gives the different notes their quality. You can read more about that, as you can see here on page 191. The other areas then we'll talk about will be the hearing and audibility limits, which are the frequencies that we can hear. The human ear can hear down to about 20 hertz and up to about 20 kilohertz. Right? You might be asked that. So we will also mention very briefly hearing protection. So hearing protection, of course, is worn to protect the ear. It says there above about 75 decibels is can be harmful. So we'll come back and talk about that in the next section. So that's it for now. Read up as far as page 192.